Velocity space. What it is and why it is needed. Velocity space should not be very difficult to explain because, at its core, it's such a simple idea. I instinctively think about special relativity by visualizing objects, observers, and light itself as it would appear in velocity space. But for some strange reason, velocity space is just very difficult to convey, even to mathematicians and physicists. This will be my best attempt at explaining what I have in mind by velocity space, and to help, I will illustrate it with a few visual examples. Velocity space is a particular way of mapping out reality, and so it's fundamentally no different from any other map that you may have seen. It's not the reality itself, but merely a method of representing an important aspect of reality in three-dimensional space. Anyone who has studied basic geometry knows what three-dimensional Euclidean geometry looks like, and would also be familiar with a Cartesian coordinate system. We start out with three orthogonal dimensions of space, with an x, y, and z axis, and one dimension of time. There's really nothing fancy about velocity space. However, within velocity space, all of the points or locations actually represent velocities as opposed to positions. This means that all distances between points in velocity space represent relative velocities. This also means that all relative velocities in velocity space represent relative accelerations, and that all relative accelerations in velocity space also represent relative jerks, and that all relative jerks in velocity space represent relative snaps, and so on ad infinitum. Anyone who has studied calculus knows what a derivative is, and velocity space is just what you get when you map out the derivative of position over time within a three-dimensional Cartesian coordinate system. Being stationary in velocity space indicates that you are in inertial motion in reality. Being in inertial motion in velocity space indicates that you are accelerating at a constant rate in reality, and so on and so forth. At any given time, everyone and everything has both a real location in ordinary space and also a real location in velocity space. When we represent objects in velocity space, we need to discard all information about position as though it were irrelevant. One really strange thing about velocity space is that almost every object, no matter how large, is just a point with no size. If the Earth were not rotating, then it would also be just a point in velocity space. And everything that is grounded on the Earth would share the same point in velocity space. However, because the Earth is rotating, the Earth actually takes the shape of a flat disk in velocity space. And the plane that this flat disk occupies is aligned with the equator. The radius of the flat disk is directly proportional to the size of the rotating object and its speed of rotation. Everything that pertains to special relativity is relatively clear when viewed through the lens of velocity space. Interestingly, just as Pythagorean theorem can be used to calculate distances in position space, it can also be used to calculate distances in velocity space, which is extremely convenient. The velocity space that I have envisioned is Euclidean. However, there's no reason why velocity space needs to be Euclidean in principle. I just prefer to work with Euclidean geometry because it's a good system to begin with as a default representation of reality. At the very least, Euclidean geometry is approximately true, even if it turns out that it's not exactly true or always true. Euclidean geometry is far simpler and more intuitive than the modified alternatives that have since replaced it. But let's not forget that the Euclidean geometry of Galileo and Newton was still good enough to get us to the moon. Through understanding velocity space as something objective which can be mapped out and visualized, the true character of the velocity of light can be made apparent. What is needed is a way to fully capture and characterize the fundamental discrepancy that is both implied and apparent whenever the velocity of light is measured or defined. This exercise will reveal both the depth of the reconciliation that is required and the inadequacy of Einstein's proposed solution. It will become clear to anyone who would otherwise have doubts that the observed velocity of light does actually depend entirely on the velocity of the observer. The use of velocity space permits both a mathematical description and a vivid visual representation of concepts which are notoriously difficult to convey with words. In addition to light, other aspects of the universe will also take on a new appearance when viewed through the lens of velocity space. The easiest way to describe velocity space is to depict it visually. Number 2, the solar system in velocity space. Let's begin with the solar system. In this two-dimensional velocity map, I have included the Sun at the center, and the circles each represent the orbits of Neptune, Jupiter, the Earth, and Mercury, respectively. The most striking feature of this velocity map is the fact that the sizes of the velocity orbits are arranged in the reverse order from how they would normally appear. The planet with the largest position orbit also has the smallest velocity orbit, and vice versa. This inversion is due to the fact that the planets which are further from the Sun orbit at a much slower speed than do the planets that are closer to the Sun. There's also another important difference between the features of the position orbit and that of the velocity orbit. At any given moment, the location of a planet along its velocity orbit will be 90 degrees away from its corresponding location in position space. This happens because the direction of motion of each planet is always at a right angle from the direction that points towards and away from the Sun. The planets are forever sliding sideways at a right angle, and so their location in velocity space is always 90 degrees ahead of their location in position space. One thing that you can see from this map is that as the planets change their position, they also change the direction of their velocity. However, their speed remains roughly the same throughout their entire orbit. Number 3, the galaxy in velocity space. The image that you see here depicts roughly what a velocity map would look like for a typical spiral galaxy, such as the Milky Way or the Andromeda galaxy. As you can see, the vast bulk of the stars in the entire galaxy occupy approximately the same velocity orbit. The reason for this is that all the stars maintain approximately the same orbital speed regardless of how far away they are from the galactic nucleus. If you find the ring-like appearance of this velocity map shocking, then you're not alone. This is the finding that eventually led to the proposal of dark matter as a way to explain how the velocities of stars could behave so differently from those of planets. And we still don't have any satisfactory explanation for why the observed stellar speeds are so remarkably consistent, and for why they appear to violate the principles of general relativity. Number 4, the expansion of the universe in velocity space. Because the universe is currently expanding in an evenly distributed manner, a three-dimensional position map of the universe and a three-dimensional velocity map of the universe should both bear a close resemblance to one another. The same pattern will also be visible for any two-dimensional cross-sections of position space and velocity space. What you see here are 8 fictional galaxies that are separated by vast distances in both position space and velocity space. These galaxies are separated by billions of light years in position space, and also by hundreds of thousands of meters per second in velocity space. The white circles that you see around each of the 8 galaxies are two-dimensional representations of manifest light bubbles. A manifest light bubble is just a way of representing the range of possible velocities that an observer can see light move at from their location in velocity space. Each manifest light bubble would be the default manifest light bubble for the inhabitants of each of the 8 galaxies. Wherever an observer travels in velocity space, that observer's manifest light bubble must also move along with them. The only way that it would be possible for the manifest light bubble of an observer to significantly deviate from their default galactic light bubble would be for the observer to achieve an extremely high velocity relative to the rest of their galaxy. Much like a shadow or a reflection, the location of the light bubble appears to track and mimic the location of the observer in velocity space. Because an observer is always at the center of their light bubble, this means that the average velocity of all of the light that they can see will overlap with their current location in velocity space. By contrast, with ordinary objects such as people, cars, planets, and stars, their locations in velocity space do not vary or depend on the location of any observer in velocity space. Dependence on the location of the observer in velocity space is the crucial difference between the apparent behavior of light and the apparent behavior of everything else. Number 5. Explaining why light moves in multiple directions at the same time. Viewing light in velocity space also makes it obvious that the multidirectional nature of light is explained by its supervelocity in combination with an observer-centered selection mechanism. The multidirectional nature of light is actually a necessary consequence of supervelocity and selection. This makes light waves very different from sound waves, for example, which do also expand in all directions simultaneously, but for very different reasons. The strong resemblance between the dynamics of expanding light waves and expanding sound waves is really just a coincidence, and it's merely a superficial resemblance. If you look at sound waves in velocity space, you will also see a sound bubble, but it will be much smaller than a light bubble. Unlike a light bubble, a sound bubble would be independent from the location of the observer in velocity space. And instead of being tied to the location of the observer in velocity space, a sound bubble is tied to the location of the medium that it travels through in velocity space. Also, there would be no distinction between manifest sound and latent sound because the manifest sound really is all of the sound. Number 6. Subjectivity versus relativity in velocity space. If the velocity of an object is subjective, then this means that different people will disagree about where to place that object in relation to other objects in velocity space. But if the velocity of an object is relative, then this means that different people will merely disagree about where to place the zero coordinates in relation to other objects in velocity space. So subjectivity has to do with an ambiguity or a dispute over where the object really is, while relativity has to do with ambiguity or dispute over where the zero coordinates should go. We should have a clear way to describe the nature of what it is that is really fixed when you're locked into inertial motion and when you're not accelerating. What is it that I share with the Earth when I'm not moving relative to the Earth? And what is it that I share with all the other objects and observers who are also motionless relative to the Earth? It's not actually a frame of reference that we share. Rather, it's a specific location on a three-dimensional velocity grid that we share. I say this because the frame of reference is just an abstract means of orienting yourself and interpreting your observations. You can easily alter your frame of reference without changing your velocity, and you can easily alter your velocity without changing your frame of reference. So, for example, if I select the Earth as an anchor for a frame of reference, and I also move relative to the Earth, then I will perceive myself as moving. But I can also shift my preferred frame of reference such that I'm stationary and it's the Earth that is moving. The shifting of the frame of reference occurs purely in the mind. Because an observer can imagine and accurately model alternative coordinate systems, they are not really bound to any default perspective, and they have the capacity to integrate information from multiple perspectives. This is precisely why nobody assumes that when they look at a light bulb, that the light is only traveling in a straight line from the bulb to their pupil. Rather, it is common sense that the light also fills up the entire room, and that other observers can also see the same glowing light bulb from other angles. Number 7. Visualizing superluminal velocity and supervelocity. The distinction between a subjective frame of reference and an objective location in velocity space is important for the following reason. Let's say that an extremely fast spaceship were to speed northwards relative to me at 200,000 kilometers per second. If that happened, then I should be correct in claiming both that the spaceship appears to be moving at 200,000 kilometers per second relative to me, and that it really is moving at 200,000 kilometers per second relative to me. I should also be correct if I say that I am moving at 200,000 kilometers per second southwards relative to the spaceship. The idea that I am moving relative to the spaceship is just as correct and verifiable as is the idea that the spaceship is moving relative to me in the opposite direction. Therefore, I am free to leave my frame of reference and occupy the frame of reference of the spaceship without ever leaving my location in velocity space. I can also reasonably take the perspective that the spaceship is stationary and that I am actually moving at 200,000 kilometers per second in the southward direction. Meanwhile, there could be a second spaceship that is moving at 200,000 kilometers per second in the northward direction. Because I am able to integrate all of this information, I can also imagine that the second spaceship would be moving at 400,000 kilometers per second northwards relative to me. In other words, I should be able to observe a spaceship that is moving at a superluminal velocity. Furthermore, if I were to shoot a laser beam in the northward direction, then I should find it incredible that this same beam of light could be moving at 299,792 kilometers per second relative to me, while also moving at 299,792 kilometers per second relative to the first spaceship, and while also moving at 299,792 kilometers per second relative to the second spaceship. By integrating all three perspectives, what I end up with is the conclusion that the same beam of light was moving at three different speeds, and so it also occupies three different locations in velocity space at the same time. These three different manifestations of the same beam of light would each be separated by a distance of 200,000 kilometers per second in velocity space. In other words, I end up with what is clearly a supervelocity. This is how it is that light can occupy a supervelocity, and this perspective is perfectly consistent with the empirical observations that have been established to date. If my frame of reference needed to be bound to my position in velocity space, then this would limit my ability to imagine and to communicate how differences in velocity space could be added or subtracted to or from one another. This constraint would also make it impossible to map out and integrate different perspectives from multiple locations in velocity space. There would be no way for me to imagine either superluminal velocities or supervelocities. But because it is possible to separate an objective location in velocity space from an arbitrary and subjective inertial frame of reference, then it is possible to see both how an object could move faster than the speed of light and how light could move at multiple speeds simultaneously. Plotting out the location of light in velocity space for different observers also makes both superluminal speed and supervelocity easy to visualize. Translating physical laws into velocity space. Under a framework of velocity space, Newton's first law of motion would be translated into the claim that all objects must remain in the same location in velocity space unless acted upon by an external force. All objects that are not moving relative to one another would share the same location in velocity space no matter how far apart they are. The speed at which any two objects are moving relative to one another is also the distance between them in velocity space. The specific direction in which two objects are moving apart from or towards one another also corresponds perfectly to the direction of the distance vector that connects them in velocity space. Einstein's theory of special relativity can also be translated into the language of velocity space. When translated, Einstein's first postulate of special relativity would state that all fixed locations in velocity space are equivalent and cannot be distinguished based on the laws of physics. Einstein's second postulate of special relativity would state that manifest light always occupies a spherical bubble with a fixed radius of c in velocity space, and with the observer always occupying the center of this bubble. Hence, the observer cannot use the relative velocity of manifest light in order to determine their location in velocity space. Velocity space gives us the basis for the selection mechanism in the supervelocity and selection theory of light, as well as an explanation for why the output of the selection mechanism is predictable. My hope is that if enough people learn how to think in velocity space, then the supervelocity and selection theory of light will be much easier to understand, and it will gain a much wider acceptance amongst those who have taken an interest in physics.